Hello everyone. It's my pleasure to introduce our work, StyleDrive, which brings driving style awareness into end-to-end autonomous driving. As autonomous driving moves toward real-world deployment, personalization becomes essential for user trust. Here, personalized autonomous driving refers to adapting decisions to a user's preferred driving style, aggressive, normal, or conservative. Although personalization has been studied in traditional modular pipelines, these methods do not scale to end-to-end frameworks. They typically rely on controlled or human-in-the-loop environments that lack real-world diversity, and they focus on isolated planning or control modules rather than full E2E learning. Meanwhile, current E2E systems mostly optimize for average performance and ignore individual differences. Ideally, personalized E2EAD should unify these two directions, but progress has been limited by a fundamental bottleneck: the absence of a large-scale real-world dataset with reliable driving style labels and a systematic benchmark to evaluate personalized models. To address this gap, as shown on the right, we introduced the StyleDrive dataset and benchmark, which provide large-scale real data, a hierarchical style labeling framework, and metrics tailored for personalized end-to-end autonomous driving. This slide summarizes the research significance and positioning of StyleDrive. From the table on the left, we can see that although many existing datasets cover diverse environments such as cities, rural areas, and highways, almost none of them offer real-world data that supports both end-to-end learning and driving style annotation. Most personalization studies are limited to human-in-the-loop simulations, while large real-world datasets like New Scenes or OpenScene do support E2E research but contain no style labels. As highlighted in the bottom row, StyleDrive is the first dataset that brings these three elements together: real-world scale, E2E compatibility, and explicit driving style supervision. The quadrant plot on the right further illustrates this. Most datasets lie on one axis, either enabling E2E or providing style labels, but not both. StyleDrive is uniquely positioned in the top right quadrant, filling an important gap in the landscape. With this foundation, StyleDrive enables two key shifts. It moves personalized autonomous driving beyond modular pipelines toward an end-to-end paradigm, and it encourages E2E systems to consider not only average performance, but also individual driving preferences. Next, I will briefly introduce how we construct the StyleDrive dataset. We build our dataset on OpenScene, which contains data from more than 16 diverse human drivers. Based on this foundation, we annotate around 30,000 driving scenes, with style preferences, covering urban and suburban roads across 4 cities in Singapore and the US. The key challenge is how to extract and label driving tendencies from large-scale real-world data. To solve this, we design a hybrid annotation framework that combines VLM-based semantic analysis with rule and distribution-based dynamic reasoning. The figure on the slide illustrates the entire pipeline, which proceeds from left to right in 3 stages: static scene modeling, dynamic scene modeling, and finally, driving style reasoning and annotation. We first enhance the HD map to obtain a static scenario taxonomy, giving us the structural context of each driving segment. Then, we model the dynamic scene using 2 information streams: VLM-based semantic attributes and traditional kinematic features. Finally, these features are fed into 2 complementary style reasoning paths, one VLM-based and one rule-based, whose results are fused and verified. This hybrid approach brings together semantic cues, dynamic behavior, and expert rules, producing reliable driving style annotations. And importantly, this annotation logic is general and can be extended to other scene understanding tasks beyond driving style analysis. This slide shows the distribution of scenarios and driving styles in StyleDrive. On the left, we see that lane following and intersections make up most of the data, while merge, lane change, and roundabout scenes add important diversity. On the right is the distribution of driving style labels. Normal behavior dominates, but aggressive and conservative styles also have sufficient coverage for learning personalized tendencies. The visualizations at the bottom provide an intuitive validation of these style differences. We show 3 representative scenarios: merging into a side road, navigating an interior road, and turning left at an intersection, and compare trajectories under different styles. The red curves indicate aggressive behavior, and the blue curves indicate conservative behavior. All examples come from locations with nearly identical layouts, and we filter out external interactions to isolate drivers' inherent preferences. Even under the same structural conditions, the trajectories diverge clearly across styles, which highlights the importance of modeling personalized driving behaviors. This page further shows how drivers with different preferences behave differently in similar scenarios. In each video sequence, the clips go from left to right, aggressive, normal, and conservative. In the left turn scenario, the aggressive driver accelerates quickly and travels the farthest, the normal driver moves steadily, and the conservative driver starts slowly with the smallest displacement. In the lane merging scenario, the aggressive driver maintains high speed and passes the merging vehicle, the normal driver slows slightly but still goes ahead, while the conservative driver leaves a larger gap or even brakes to yield. These examples clearly demonstrate that driving preferences naturally result in distinct behaviors, even under nearly identical scene conditions. Now I will introduce the StyleDrive benchmark. It is built on the NavSim simulation environment, which supports local process simulation under open-loop testing. We extend the original PDMS metric in NavSim to a style-modulated version, SMPDMS, to reflect that drivers with different preferences perceive driving quality differently. We adjust three key submetrics. EP modulates vehicle progress according to the desired level of assertiveness. Comfort adapts its thresholds based on sensitivity to physical disturbances. And TTC adjusts collision time tolerance according to the driver's risk preference. These modifications allow the benchmark to evaluate how well a model matches a target driving style. For evaluation, we include 4 representative E2 EAD models and create style condition variants of each. Driving preference is encoded as a one-hot vector and injected into the trajectory prediction head or query tokens, enabling explicit conditioning on the desired driving style. This slide summarizes the main benchmark results. In the top table, we compare 4 representative E2 EAD models in their original forms and in their style condition variants. For transfuser, WOTE, and diffusion drive, adding style conditioning consistently improves SMPDMS, showing better behavior alignment with the target style. Diffusion drive style achieves the highest overall score, improving SMPDMS from around 79 to over 84. The only exception is ADMLP, whose simple architecture lacks the perceptual capacity to effectively use style inputs. At the bottom of the table, we further ablate diffusion drive style by forcing fixed, aggressive, normal, or conservative tendencies at inference time. Moving from aggressive to conservative, NC, DAC, TTC, and comfort scores all increase, while EP peaks under the normal setting, consistent with the dominant distribution of normal behavior. These results verify the driving style is controllable and reflected in the model's behavior. On the lower left, the L2 open-loop trajectory errors show that style-conditioned models generally predict trajectories closer to human demonstrations, indicating more human-like behavior. Finally, the table on the lower right tests whether our metric is truly style-sensitive. Compared with the original PDMS, SMPDMS exhibits larger variation across style-conditioned models while maintaining overall stability, confirming that it better captures style-specific behaviors. This slide further shows how diffusion drive style responds when we change only the style input while keeping the scene and model weights fixed. Each row corresponds to the same scenario. On the left, we compare aggressive versus normal, and on the right, conservative versus normal. The red curves are the model's predicted trajectories under the given style, and the green curves are human demonstrations. Across all cases, the pattern is very clear. With an aggressive style, the model takes more assertive and decisive actions. With a conservative style, it becomes more cautious and leaves more space. These visualizations show that the model reacts consistently and interpretably to different style inputs, demonstrating strong controllability. To conclude, StyleDrive makes 4 key contributions. We provide the first large-scale real-world dataset for personalized end-to-end autonomous driving. We introduce a hybrid annotation method that combines VLM analysis with rule-based reasoning for reliable driving style labeling. We build the first benchmark for personalized E2 EAD with the SMPDMS metric system, which adjusts evaluation according to user preferences. And our experiments show that style conditioning substantially improves behavioral consistency, demonstrating the value of personalized E2 EAD. Looking forward, several directions remain open. We aim to construct finer-grained hierarchies of driving styles, explore unified models that jointly capture scenes and style preferences, and leverage user profiling to infer preferences automatically for real-world deployment. Thank you for your attention. I'm happy to take any questions.